So in the previous video we were discussing about the types of the light sources. Next is the directional light source and spotlight effect. A local light source can be modified easily to produce a directional or spotlight, a beam of light, which is called as beam of light. So spotlight, the structure of the spotlight, let us see later. If an object is outside the directional limits of the light source, we exclude it from the illumination by that source. Okay, one way to set up the directional light source is to assign it a vector direction and an angular limit, say theta, measured from the vector direction in addition to its position and color. We can denote V is the vector notation, okay, V light as a unit vector in the light source direction, and V obj again a unit vector in the direction from the light position to an object position. Okay, this is what the relation they are saying, the dot product between two vectors V obj and V light dot product, which is equal to cos alpha they are saying. So just go through this diagram, you will understand the structure of the spotlight. So spotlight, how does it look? So see, a conical structure, so a closed surface, a kind of closed surface where there is a light source here. The look at the pointer, see, there is a light source is fixed in this position. So what is the area, of intensity? The light source can propagate only within this region or this boundary, isn't it? So beyond that it will not. So kind of a closed surface is defined for that, isn't it? So another important thing you have to remember here is the intensity, that also matters. So there are angle different, there is a various or a different angle of illumination to be considered, right? Along the boundary it is different, at the midpoint it is different, and so on. So illumination function to be discussed. So vector, I'll just go through the contents of it. I'll just delete the things what I have marked. Hope it is visible now. Theta, right, is the angular displacement, theta 1 or theta I, whatever you call it, as well as V light, the light direction vector. Actually V light or light direction vector is the midpoint, exactly the midpoint of the conical surface. Okay, a line drawn which is called as V light vector notation, and here is an angular displacement theta, right, between the between one of the boundary and the line or the vector what you have defined as the defined through the midpoint. Fine, just go through the meaning of alpha they are describing here, where the angle alpha is the angular distance of the object from the light direction they are saying. Fine, if we restrict the angular extent of the light of any light cone so that the angular displacement theta l, okay, light or theta you call just it in between the range 0 to 90 degree, then the object is within the spotlight. It is considered as the object is within the spotlight. There is a condition to be satisfied if cos alpha is greater than or equal to cos alpha is greater than or equal to cos of theta l, which is shown here. So this is called as the object in the range of spotlight. See, so this entire portion is marked here. Okay, see the portion which is see what is alpha is defined here, cone axis vector, and see the two vectors are defined. The angular displacement between both is marked as alpha, and theta is fixed, that is the angular displacement between the boundary and the midpoint, and one more vector is taken to the object, so which is considered as the one of the point of the object vector is drawn from the light source, right, and the angular displacement between the midpoint and the line what you have drawn, the vector representation for the object, which is marked as alpha. Okay, you can find that in the particular diagram, in this particular diagram. So for the spotlight, angular intensity attenuation is the, for a directional light source we can attenuate the light intensity angularly about source as well as radially out from the point source position, which we have seen earlier. This allows intensity decreasing as we move further from the cone axis. A commonly used angular intensity attenuation function. Let us see that function later. You just try to understand this, right? For this is a directional light sources. A conical structure is there, so we can attenuate the light intensity angularly about the source as well as radially out from the point source position. This allows intensity decreasing as we move further from the cone axis. So intensity is maximum. Intensity is maximum where intensity is maximum in this direction, where slightly reduced towards the yeah, as we move towards the border, the intensity will be slightly reduced. It is observed maximum at center position. Okay, fine. So commonly used angular intensity attenuation function for a directional light source. This is what the formula: intensity attenuation function phi, f of phi it is called as. This is for this notation is used for uh, cone structure in the sense spotlight. Okay, cos of phi to the power alpha, where phi lies between 0 and theta. That is what they are. Yeah, cos of phi to the power a1 it is. Hope it is not visible, which will be sorry, cos of al phi it is. Oh, the exponent, the attenuation, where the attenuation exponent is al is the notation they have used, this one. Okay, anything you can even use a also, not an issue. Al, that is al. Okay, cos phi to the power al, where the attenuation exponent al is assigned some positive value, that is and the angle phi is measured from the cone axis. Fine. The greater the value of the attenuation exponent al, the smaller the value of the angular intensity attenuation function for a given value, that is angle phi, which is greater than greater than 0 degree, because phi ranges between 0 degree and theta. That is what they have mentioned here, right? Okay, fine. You have to keep all these functions in your mind. We'll be using them further in our next discussion. Okay, uh, that is all about the spotlight. We'll continue our discussion in the next video. Watch the videos repeatedly. Please note down the equations as well.